Welcome to the course on advanced machining process. Today we shall continue that electrochemical machining process. So already we have discussed the working principle of electrochemical machining process. Today we shall discuss some hybrid machining process using electrochemical machining concept. So first we shall discuss electrochemical grinding process. So already we have discussed that hybrid process means here we shall combine one non-traditional machining process and one conventional machining process. In electrochemical grinding process, we combine that electrochemical machining plus grinding operation. So it is a electrochemical grinding operation. So we shall start with electrochemical grinding. So electrochemical grinding is an electrolytic metal removal process involving negatively charged abrasive grinding wheel, a conductive fluid electrolyte and a positively charged workpiece. Workpiece material depletes to the electrolyte solution. Electrochemical grinding is similar to ECM except that the cathode is a specially constructed grinding wheel shaped like the contour to be machined. So what is the conventional grinding wheel? In conventional grinding wheel, these abrasive particles are actually bonded together in a bonding material, like resin bond, like in a bonding material, it is bonded together. And so workpiece material, so for workpiece material may be electrically conducting or electrically non-conducting material. So any kind of material can be polished by normal conventional grinding operation. And conventional grinding gives good surface finish and low tolerance value. So, but it produces bars. So after means what about after grinding operation, you will see there are bars formation at the edge. Also there is a heat affected zone is there in conventional grinding operation, and also there are thermal residual stresses are there because it is a shearing operation by abrasive particles from the workpiece material. So there is a deformation takes place during shearing operation by these abrasive particles in conventional grinding operation. So there is a bars are formed, and then there is a heat affected zone is there. So these are the disadvantage of conventional grinding operation. And another disadvantage is that there is a thermal residual stress is generated on the workpiece surface. Okay. So in case of conventional grinding, 100% material removal takes place by the abrasive action. So by shearing by these abrasive particles, totally 100% removal by abrasive action. But in case of electrochemical grinding operation, 90% of the material removal is by grinding operation and 10% of the material removal is by 10% of the material removal is by grinding operation and 90% of material removal by electrochemical machining operation. So these are the two views, two pictures of first one is the normal conventional grinding operation and second one is the electrochemical grinding operation. So in first case you will see that there is a up grinding here. So this is the contact arc length here. So here this contact arc length, it is in contact. So this grinding wheel, these abrasive particles are totally in contact with the workpiece material here, you can see here. But in this case you can see, so there is a rotation of this grinding wheel. Okay, so there is a rotation of the grinding wheel in case of electrochemical grinding operation. So here there is a decreasing gap. So initially this gap between this wheel and workpiece is more. Here you can see wheel is more, and this gap is actually it is reducing in case of electrochemical grinding operation. And after that in this zone you can see it is totally, in this zone it is totally actually this grinding wheel in contact with the workpiece. So initially you can see there is a no contact between the grinding wheel and the workpiece. Okay. So there are three different zones are there, three different machining zones are there in case of electrochemical grinding operation. So this kind of decreasing gap is not visible in case of conventional grinding operation. So in conventional grinding operation, this grinding wheel, it is totally in contact with the workpiece material. But in case of electrochemical grinding, there is a little bit of gap is there in between this grinding wheel and the workpiece. So in electrochemical grinding, workpiece should be electrically conductive. So that is the main constraint. So but in normal conventional grinding, any kind of workpiece, whether it is electrically conducting or non-conducting, can be machined by this process, by conventional grinding operation. But in case of electrochemical grinding operation, that workpiece material should be electrically conductive. So electrolyte is used during electrochemical grinding, and after proper filtration, it is recirculated. So in electrochemical grinding operation, this grinding wheel and the workpiece, it is dipped inside the electrolyte chamber, and same electrolyte is recirculated. So as it is recirculated, it should be filtered during machining operation, during electrochemical grinding operation. Otherwise, whatever debris particles are there, it will be there in between this inter-electrode gap. Okay, so that's why this electrolyte, this property also changes, because of sludges, it comes into the electrolyte, so it has to be filtered. Okay. So in case of electrochemical grinding, the bonding material of the grinding wheel should be electrically conductive, but which is not there in case of conventional grinding operation. In conventional grinding operation, this bonding material is not electrically conducting. But in case of electrochemical grinding, metallic bonding material is used, so that this bonding material should be electrically conducting. So for electrochemical grinding wheel, bonding material should be electrically conductive. So grinding wheel act as a cathode. So in electrochemical grinding machine, so grinding wheel, it acts as a cathode, and a workpiece acts as a anode. So material removal takes place by electrochemical dissolution, by electrochemical machining is 90%, and 10% material removal is by mechanical ablation or mechanical shear. So you can see here 90% by electrochemical ablation or anodic dissolution, and 10% is mechanical ablation. So high material removal rate is achieved in case of electrochemical grinding operation. So it is very obvious. So these abrasive particles in electrochemical grinding operation, these abrasive particles which is actually protruding from the grinding wheel acts as a barrier. So it acts as a inter-electrode gap. So it acts as a barrier in between this grinding wheel and the workpiece. So it acts as a barrier, so it does not allow this grinding wheel metallic bonding material to touch the workpiece surface, because these abrasives which are protruding from the grinding wheel, it acts as a barrier. Okay. So it does not allow this metallic bonding material to touch the workpiece surface. Okay. So inter-electrode gap is already it is maintained. Okay. So height of the abrasive particles protruding outside the bonding material of the wheel maintains constant inter-electrode gap. So these abrasive particles are acting as a spacers. So these abrasive particles are acting as a spacers. So that's why, as only 10% machining is by the mechanical ablation and 90% by electrochemical grinding operation. So there is a high wheel life which is expected from electrochemical grinding operation. So if you consider this conventional grinding and electrochemical grinding, in electrochemical grinding, wheel life is more than 10 times than the conventional grinding operation. Because in electrical grinding, there are only 10% mechanical ablation is there. So commonly used electrolytes in electronic grinding is sodium chloride NaCl solution or sodium nitrate solution. So these are the commonly used electrolytes which is used during electrochemical grinding operation. So you can see this is the working principle of electrochemical grinding operation. So this is the grinding wheel which is rotating here. So this grinding wheel which is rotating in the anti-clockwise direction here, and here this workpiece actually it is moving from left to right. Okay, so this is the, it is like a down milling operation. So it is like a down milling operation. Already I told there is a decreasing gap. So inter-electrode gap, if you see here, inter-electrode gap is more here, and while coming to this point, it is inter-electrode gap is reducing. So from here to here, inter-electrode gap is reducing. Okay. So here so there are three different zones are there. So this is zone 1, this is zone 2 and 3, and this is the zone 3. After that, this much material is removed. So this much material is removed from this process. So individual zones are actually shown here. So this is zone 2, you can see this is the zone 1, you can see here. So in zone 1 only this electrochemical machining predominates, because here this grinding wheel does not touch the workpiece material here. So in zone 1 this grinding wheel does not touch the material here, workpiece material here. So only there is a electrochemical machining operation which or anodic dissolution is there in zone 1, because this particles, this grinding wheel does not touch the workpiece surface, because there is a decreasing gap in the zone 1. But in zone 2 we can see there is this abrasive particles or grinding wheel, it touches the workpiece surface. So here both electrochemical machining and grinding operation, both mechanical abrasion, both takes place. Okay. So in zone 2. However, in zone 3, if you see in zone 3, again this abrasive wheel, grinding wheel actually it is lifted from the workpiece material. So it is lifted there. Again it does not touch the workpiece surface in zone 3. So in zone 3 also there is abrasive particles, or there is no mechanical abrasion, only that electrochemical grinding, electrochemical or anodic dissolution or electrochemical machining operation is there in zone 3. So in zone 1 electrochemical grinding, a little bit of mechanical abrasion is there, but in zone 2 mostly this electrochemical grinding, electrochemical operation and mechanical abrasion both are there, and in zone 3 only this anodic dissolution is there in zone 3. So in zone 2 you can see here, in stage 2 you can see there is this is one abrasive particle, this is one abrasive particles is there, and bonding material of the wheel, which is metallic bonding material, so that is negatively charged, cathode. So grinding wheel it is negatively charged, it is cathode, and workpiece it is anode here. So in between these two abrasive particles you can see this electrolyte, it is making a small cell here. You can see there is a small cell is here, small electrochemical cell it is generated. So in that shell actually by electrochemical machining operation or by anodic dissolution material is removed from the workpiece surface. So you can see here in this stage 2 there is a small cell electrochemical grinding, electrochemical cell, small cell is there. From that cell actually machining is going on by electrochemical machining, and also at the same time these abrasive particles are touching to the workpiece surface. Okay. So by mechanical abrasion also material is removed from the workpiece material. So there are two processes in stage 2, by electrochemical operation or anodic dissolution plus mechanical abrasion, so which is visible in this figure. So here we can see in phase 1 this much of material is removed by phase 1, material removed by phase 1, and this much material is removed by phase 2 and phase 3. So most of the materials are removed in phase 1 here, and in phase 2 this much of material is removed in phase 2. So here you can see this inter-electrode gap, that is a decreasing trend in between this grinding wheel and the workpiece. So the gap is actually reducing here, and here actually it is touching, at this point it is touching to the workpiece surface. So this is the metallic bonded grinding wheel, this is the workpiece here, there are 3 zones. zone 1, zone 2, and this is zone 3. And different zones, there are different kind of material is removed. So, electrochemical grinding finishing area, there are 3 zones already I told. In zone 1, it is purely electrochemical dissolution takes place. So, purely electrochemical dissolution takes place in zone 1. So, there is a wheel rotation is there. Because of this wheel rotation, it drags the electrolyte into the inter-electrode gap. So, because of this rotation of this wheel, it drags the electrolyte into the inter-electrode gap in zone 1. Okay, so that is because of dragging of this electrolyte there, and at the same time electrochemical dissolution is there. So, these hydrogen gas bubbles are evolved at the cathode. Also, there is a mechanical metallic sludges are actually generated. So, because of this metallic sludges or debris or whatever machine products actually, these mechanical sludges, a little bit increase the electrical conductivity. But whatever these hydrogen gas bubbles are generated, because of that, this electrical conductivity of the electrolyte actually it reduces. So, this both phenomena actually happens there in this zone 1. So, because of this contamination of this electrolyte in zone 1, because of this machining operation happens there. So, overall this electrical conductivity of the electrolyte reduces. Okay. So, contamination of zone 1 takes place by reaction products and gases. Electrolytes electrical conductivity K reduces there. So, electrolytes gets trapped between the abrasive grit and workpiece surface, and it form a electrolytic cell also. Okay, so electrolytes get trapped in between these two abrasive particles and the workpiece. So, it forms the electrolytic cell, small electrolytic cell. So, as the electrical conductivity reduces, electrolytes electrical conductivity reduces. So, this inter-electrode gap also then reduces. Inter-electrode gap also reduces in zone 1. So, that is why this wheel comes closer from inter-electrode gap from a higher value, it comes closer to the lower value at the end of zone 1. Okay. So, small amount of material is removed in this zone. So, here inter-electrode gap is comparatively high, and mostly this material removal takes place because of this electrochemical dissolution in this zone. In zone 2 actually this pressure is high because this electrolyte, because this grinding wheel is rotating with a very high RPM, 1200 to 1800, 1200 to 1400 meter per minute, this peripheral velocity of this grinding wheel. So, it is rotating at a very high RPM. So, because of that actually huge amount of pressure actually generated in zone 2. So, also there is a converging gap there. So, there in this zone 2 actually this abrasive grinding this grinding wheel and the workpiece, it comes very closer. Okay, so these abrasive particles are touching to the workpiece surface in that zone. So, because of this converging gap in that zone, higher pressure exists. So, pressure pressure on the electrolyte is more in that zone 2. So, it suppresses the formation of the gas bubbles. So, whatever gas bubbles are there, it suppresses. It does is because of this high pressure, this formation of this hydrogen gas bubbles actually suppressed. So, because of this less formation of these hydrogen gas bubbles, because of this high pressure of this electrolyte in that zone, so electrolytes electrical conductivity will be more in that zone, in zone 2, electrolytes conductivity, because there is no formation of hydrogen gas bubbles because of this high pressure. So, electrical conductivity of the electrolytes, electrical conductivity will be more. Okay. So, material removal rate will be high, because this higher the electrical conductivity of the electrolyte, more material will be removed by electrochemical dissolution. So in this zone actually these abrasive particles also touching to the workpiece surface. So in this zone abrasive grains abrade the surface. As a result they remove material from the workpiece, and oxide layers also, whatever oxide or precipitation layers are generated on the workpiece surface, these oxide layers also removed in this zone 2, because these abrasive particles are touching to the workpiece surface. Also in this zone, these abrasive, in between these abrasive particles and on the workpiece, there is a tiny small cells, electrochemical cells are generated, are formed. From these electrochemical cells, material is removed by electrochemical dissolution or anodic dissolution. So material used in the form of small chips here. So oxide layers removal of helps in electrochemical dissolution, because this passivation layer, because of this in electrochemical or any chemical process, that is a passivation layers are generated. This passivation layer has to be removed to come to the face metallic surface exposed to the electrolyte. To make the fresh metallic surface exposed to the electrolyte, so this oxide layer or passivation layer has to be removed. As the abrasive particles are removing the passivation layer in zone 2, fresh metals actually coming out in front of this electrolyte, so more machining will be there. So that's why it is called mechanical assisted electrochemical grinding process, because here more material removal is in zone 2 by electrochemical dissolution and also mechanical grinding operation. Now come to zone 3. Now in zone 3 actually suddenly this it is lifting. So this grinding wheel is lifting from the workpiece surface. Now pressure is also released now in this zone, but these abrasive wheels also not touching to the workpiece surface. So grinding wheel also not touching to the workpiece surface, it is lifting from the workpiece surface. So in this zone also material removal is by electrochemical dissolution only anodic dissolution only. Okay. So in this zone there is no contact between the abrasive grain and workpiece surface. Wheel starts lifting off from the workpiece surface, hence material removal takes place by electrochemical dissolution only. And electrochemical dissolution removes scratches and bars formed in zone 2. And whatever bars and scratches formed in zone 2 by abrasive particles, it is removed in zone 3 by electrochemical dissolution. So electrochemical dissolution removes scratches and bars formed in zone 2 on the workpiece surface. So now this is the electrochemical grinding machine tool. So you can see here, this is the grinding wheel here, metal bonded grinding wheel, which is negatively charged, which is connected to the cathode or negative charged here. So there is an nozzle here. So this nozzle, this working of this nozzle actually, it flows the electrolyte in between this grinding wheel, periphery or surface and the workpiece. In between that inter-electrode gap, it flows the electrolyte into the inter-electrode gap. Now this grinding wheel, this is the grinding wheel shaft. So it is a rotating shaft. So now this grinding wheel shaft, it is negatively charged. So how to give current to this negatively charged current to this shaft? So there are two different ways you can give current to this shaft here. So either you can use a brush here. So you can use a brush. Generally in the market these graphite brushes are there. Using these graphite brushes you can use, you can give current to this grinding wheel shaft, or you can dip this shaft inside a mercury container. So inside a mercury container you can dip this shaft, and there because this mercury it is electrically conducting material. Okay, so you can flow the current to this shaft by these two different ways, either brush or mercury dipping. So this is the DC power supply here. So from this DC power supply, this negative one, it is connected to the grinding wheel, and this positive terminal, it is connected to the workpiece. Okay. So now here through this nozzle, you are giving this electrolyte, flowing that electrolyte at the inter-electrode gap, and both the grinding wheel, part of the grinding wheel and the workpiece, it is dipped inside the electrolyte chamber. Okay, so as the wheel is rotating with a high RPM, this effective flowing of electrolyte at the inter-electrode gap can be ensured. So that is a flow meter and pump, and then there is a this fluid. It is also cleaned. Okay, filtration system is there. After filtering, actually it is flown through the nozzle here. So that is this wheel, and this electrolyte, it is recirculated during electrochemical grinding operation. So you can see here this carbide tip of a cutting tool. It is actually sharpened. Okay, so this carbide tip is sharpened here. Through this nozzle, you can see this at this inter-electrode gap. This electrolyte is flown at this inter-electrode gap. So here actually it is through these brushes, actually in this shaft, grinding shaft, we are giving current using this brush, current to this shaft. So this is the electrode here again. It is a conducting bonded, metal bonded grinding wheel. Okay, so this is the container here. Inside this container we kept our work table here. On that work table this carbide tip is kept. So in between this carbide tip and this grinding wheel, there is insulating abrasive particles are there. So it is making the gap between this grinding wheel and the workpiece material. It maintains the gap. So these abrasive particles. Okay, so there is a filtering system is there. So as the electrolyte is recirculated, it should be filtered properly, and through pump it is again flown through the nozzle here, and there is the DC power supply here. So machining area are made of non-corrosive, because total machining area electrolyte is there. So this electrolyte, it is corrosive electrolyte is used. So total machining area has to be made of non-corrosive material. So this machining area, all the components in the machining area are made of non-corrosive and electrically non-conducting material. Okay. Power supply to the grinding wheel is given either through brushes or through mercury coupling, and if you are using mercury coupling, it can carry more current also. So there is a low probability of short circuiting, because protruding abrasive maintain the inter-electrode gap between the workpiece and the wheel bonding material. So there is no need of short circuit protection circuit. So there is no need of short circuit protection circuit in case of electrochemical grinding, because these abrasive particles are maintaining the gap in between this grinding wheel and the workpiece. So there is no need of short circuit protecting circuit. So there will not be any short circuit during machining. So there are different kinds of grinding operation, electrochemical grinding operations are available. Like cylindrical grinding, you can see here, this is the cylindrical grinding. Form grinding, using form grinding, any kind of geometry you can generate into the workpiece surface. So that is called form grinding. So in that case, we shall use form grinding wheel. That is a phase grinding operation is also there. Top plate of the workpiece can be polished or finished by phase grinding operation, or internal grinding. So you can do the internal grinding also. Okay, so electrochemical cylindrical grinding. So this is the slowest because the smallest contact area between the workpiece. Suppose this is a cylindrical grinding operation here. So only this portion here actually it is in touch with the workpiece surface. So that's why this is the slowest process. Small contact area between workpiece and the grinding wheel. Phase grinding actually it is the fastest process because it has a largest contact area between workpiece and the grinding wheel. Now bonding material. So what kind of bonding materials are used for this grinding wheel? So you can use copper, brass, nickel or copper impregnated resin also you can use as the metallic bonding material in case of electrochemical grinding operation. So now dressing is also required because as the machining, as the 10% there is a mechanical abrasion is there. So whatever these abrasive particles, whatever the tiny chips are actually generated, it may clog into the grinding wheel. So then its performance will be reduced. So for doing that thing, for dressing operation, reverse the current and do the electrochemical grinding on a scrap workpiece. Okay. So in normal case actually this grinding wheel it is cathode and workpiece is negative. But in case of during dressing operation, what you have to do? You have to change the polarity of the grinding wheel and the workpiece. So in that case, your grinding wheel will be positively charged and your workpiece will be negatively charged. Okay. So in that case, what will happen? Material will be removed from the metallic grinding material by anodic dissolution. Okay. So then fresh abrasive particles will come outside. Okay. So reverse the current for dressing operation, reverse the current and do the electrochemical grinding operation on a scrap piece of workpiece. So in that case, that fresh abrasive particles will come outside. So it will deplete the metal bond exposing the abrasive. So commonly used abrasives are aluminum oxide, its size 60 to 80 micron size is used, blade size is 60 to 80 micron. Frequent wheel dressing is not required like in normal grinding operation. So because in process screwing of the metal bonded grinding wheel during electrochemical dressing due to the dissolution of bonding material. So that's why it does not need mechanical shear. So mechanical shear is unnecessary. And what kind of electrolyte is used? Electrolyte should be electrically or chemically inert to conductive wheel bond material and workpiece. So electrolyte should be chemically inert to conduct wheel bond material and workpiece. So what are the process characteristics? Material removal rate and surface finish depends on the process parameters like wheel speed. At what RPM we are rotating that wheel. So what is the wheel feed or workpiece feed rate in case of fixed grinding wheel. Electrolyte type, concentration of this electrolyte, delivery method, pressure, current, density, etc. So these are the different process parameters. So higher current density, if we want to get high material removal rate and high surface finish, better surface finish. So in that case, you have to apply high feed rate. High current density will increase the material removal rate as well as surface finish. It will improve the surface finish, also it will increase the material removal rate. But if we increase the voltage, so in case of if we increase the voltage more than 4 to 15 volt, in that case, lead to sparking, so it leads to sparking at the wheel. At the front of the wheel, it leads to sparking and deteriorate the surface of this surface finish and damages on the grinding wheel. So it deteriorates the surface finish and damages in the grinding wheel. So in case of electrochemical grinding operation, material removal rate as high as 10 times higher than the material removal rate in conventional machining for a 65 HRC workpiece. So it is a bulk process, it is a cold process. So here this temperature does not go beyond 100 degrees centigrade, because whatever this temperature is generated, because this electrolyte is forced to flow in between this grinding wheel and the workpiece, so this temperature actually it is automatically controlled. Okay, so whatever this heat is generated, it is taken outside. Okay, so it is automatically, temperature is automatically controlled. So it does not go beyond 100 degrees centigrade. So if it goes beyond that, then there is a structural damage or grinding cracks may be generated. So poor fatigue strength is observed in case of electrochemically grinded workpiece, because that is stray cuttings are there by the grinding wheel. So because of the stray cuttings are there, the small pits are actually generated on the machine surface. So due to the stray cutting current attack leaves the series of pits on the workpiece surface. It acts as a sites for fatigue crack initiation. So it acts as a sites for fatigue crack initiation. So machining condition, if we give high feed rate, in that case than the required one, okay, premature detachment of the abrasive will be there. So because these abrasive particles will be more loaded there, in that case if we give more feed rate, so there will be premature detached abrasive will be there. So it will lead to the excessive grinding wheel wear. So grinding wheel will wear out, because if we give more shear, more feed rate. So inter-electrograph generally 0.25 millimeter for a freshly dressed wheel. Abrasive particles maintain the electrical insulation between the cathode and anode, and determine effective gap between them as low as 0.025. So wheel surface speed is 1200 to 1800 meter per minute, and depth of cut it is below 2.5 millimeter. So it is limited by the wheel contact arc length. So it is limited by the wheel contact arc length. So contact arc length already we have shown there. So this is the contact. So this is the contact arc length. So if we increase the feed, this contact arc length increases. As the contact arc length increases, limited to the wheel contact arc length should not be exceed 19 millimeter. If the contact arc length between the grinding wheel and the workpiece it is more than 19 millimeter, in that case electrolytes become ineffective due to the higher concentration, because contact arc length if it is increasing, okay, so more hydrogen gas bubbles will be generated. Okay, so electrolytes become ineffective in that case due to the higher concentration of hydrogen gas bubbles and sludge formation. So current generally it is maintained in between 50 to 3000 RPM, 3000 ampere. So in between this 50 to 3000 ampere, in between this current is maintained in case of electrochemical grinding operation. So if feed rate is lower than the required one, in that case what will happen? Large overcut will be there. Okay, so if it is lower than the required one, then in that case large overcut will be there, or pore tolerances will be there, and pore surface finish will be achieved. And if we decrease the feed rate beyond a lower value. So these are the process performance. Base tolerances obtained by this process is plus minus 25 micron. Minimum outside corner radius is 0.025, but minimum inner radius, corner radius is 0.25 only. So surface roughness that can be obtained 0.12 to 0.8 micron. So workpiece surface there is no burrs, there is no scratches are there. Burrs and scratches get dissolved in the zone 3 by electrochemical dissolution. So there is a very reduced risk of thermal damage because temperature does not go beyond 100 degrees centigrade. And whatever heat is generated is carried away by the electrolyte. So cost of machining in case of electrochemical grinding is very less because here in electrochemical grinding material removal rate is very high than normal grinding operation. So that's why cost of machining is very high in case of electrochemical grinding operation. Cost of machining is less in case of electrochemical grinding operation. So cost of machining by conventional grinding operation is more, and cost of machining in case of electrochemical grinding operation is less. But electrochemical grinding machine tools are actually costlier than conventional grinding operation. Okay. So these are the applications for this electrochemical grinding operation. So it is used for grinding of carbide cutting tools. Okay. So it is economical in grinding carbide cutting tools. Electrochemical grinding cemented carbide workpiece, no damage to the microstructure, no micro cracks or any other defects are there. For reprofiling owned locomotive traction gear, wear marks removed from the gear tooth surface by removing 0.38 millimeter thick layer of material from the gear. And it does not, the gear hardness actually does not affect the machining process. So it is also used for bar-free sharpening of the hydrodynamic needle, this electrochemical grinding. So grinding of super alloy turbine blades, form grinding of fragile aerospace, honeycomb structures of metals, actually it is done by this electrochemical grinding operation. So now we shall start with another process, that is another hybrid process, that is called electrostream drilling operation. So this kind of electrostream drilling, so it is used for high aspect ratio holes. Suppose if you want to make a holes of 40:1, this much of high aspect ratio holes with a small diameter holes you want to maintain. So in that case, this kind of electrostream drilling operation can be used. So in conventional electrochemical drilling operation, hollow metal tubes are used as the cathode. So electrolyte flows at high velocity through this hollow tube, and cathode penetrates in the hole, and hole diameter, in that case this hole diameter is greater than the cathode diameter, because through the hole, through the tool, metallic tube, actually you are flowing the electrolyte with a very high velocity and it is coming outside. Okay, so outside actually because of this stray cutting, it will become stray cutting by this electrode, metallic electrode. This diameter of the hole which is made by this process will be higher than the cathode diameter. So for drilling of a very small diameter hole with a high aspect ratio, this kind of electrostream drilling operation is utilized. Thousands of small cooling holes in nickel, cobalt and super alloys can be made by this process. High velocity negatively charged acidic electrolyte is used. Because acidic, in case of normal Eastern process, whatever these metallic hydroxides are there, actually it does not react with the electrolyte. It precipitates into the electrolyte, so it does not react with the electrolyte. But in case of electrostream drilling operation, acidic electrolyte is used. So whatever these debris particles are generated, metallic hydroxides are generated, it dissolves. It is dissolved into the, these metallic hydroxides are dissolved into the acidic electrolyte. So as it dissolves into the electrolyte, so it does not clog in between this inter-electrode gap. Okay, so that's why you can generate any kind of hole, any dimension of the hole you can generate. So using this electrostream drilling, thousands of small holes can be made in nickel, cobalt and superalloys. High velocity negatively charged acidic electrolyte, stream of acidic electrolyte is used, and diameter of the holes are generated 0.127 to 0.89 millimeter, and voltage applied 150 to 850 volt. So this much of voltage is applied. So this is the schematic diagram of the electrostream drilling operation. So here you can see, in electrostream drilling operation we don't use any metallic tube. So here actually non-conducting material, generally glass, is used as a nozzle. So this stream of electrolyte with a high velocity, it is flowing through this nozzle. So this nozzle actually, its diameter is as less as possible, and it is given it is faded towards the workpiece surface. Okay, so that's why this small intergalactic gap is maintained, and acidic electrolyte is used. This acidic electrolyte, after impinging into the workpiece surface, material removal rate will be there. So it will start removing material from the workpiece material. So this exhaust fan is required actually, because from this zone, whatever this volatile material is, whatever these gas bubbles are generated, so these gas bubbles are actually, it is released from this exhaust fan. So this is the excited view of the machining. So you can see through this hole actually, through this glass tube, this acidic electrically charged acidic electrolyte is coming, and it is going outside. So there is a heater is there inside this container, electrolyte container, to maintain the temperature at a certain value. So there is a filter is there. Through this filter actually this electrolyte is passed. So while passing, it will remove the debris particles of metallic hydroxide. So motion control is given to this workpiece, and here this tool is actually kept fixed. So there are two different processes there. One is dual drilling, another one is the penetration drilling. Dual drilling is used when this nozzle actually it is kept fixed. And penetration drilling, in case of penetration drilling, this nozzle actually it is not fixed, it is given a certain feed towards the workpiece surface. Okay, so when there is a zero feed rate to this nozzle, then it is called dual drilling. This dual drilling actually it is done for shallow holes. For shallow holes it is done. Shallow and less accurate holes, this dual drilling is done. So limited depth of hole and accuracy. Workpiece configuration and machine capabilities do not allow the nozzle movement. And maximum depth can be machined by this process is 5 millimeter. But in case of penetration drilling, as the nozzle is actually, it is coming towards the, it is fed towards the workpiece. So here this deep and accurate drilling can be possible. Constant gap using finite feed rate. So constant gap is actually maintained using a finite feed rate. So a gap sensing device is used to maintain the constant gap. Maximum depth can be machined is 19 millimeter, and machining rate is 1.5 meter per minute. So now this kind of holes you have to make. So for making this kind of holes, this electrostream drilling operation is the only solution. Here this diameter of the nozzle actually it is reduced here, it is further reduced, and also there is a sufficient space is there to insert this electrolyte, to insert, there is a sufficient gap is available to insert this electrolyte inside the tube. So this tube actually this front portion of this tube actually it is bent and it is forwarded inside this hole. Okay, so this much of hole can be generated. So length of the bent tube is more than the thickness of this wall. So this kind of small holes perpendicular to this wall, it is generated by the electrochemical machining or electrostream drilling operation. So this drilling a hole in cavity, tool with the straight angle bent at tube, length of the small part of the tube is greater than the depth of hole. So this is the depth of hole. Outside diameter of the nozzle tube should fit within the hole being drilled, allow room for repeatable escape of used electrolytes. So electrostream, this is the electrostream drilling, there is no bars are generated, no residual stress is generated, and temperature it is maintained up to 100 degrees centigrade. So that's why there is no heat affected zone, insignificant heat affected zone. There is no tool wear, bell mouth hole is generated, multiple hole drilling, nozzle it is made of glass tubing, machine and fixture acid resistant materials are used. So this is the acid resistant material is used for machine and fixtures. So charging of electrolyte, how to charge the electrolyte? So you can use a metallic sleeve or you can use a titanium wire. So this titanium wire it is fed towards the mouth of the hole. Okay, so it is fed towards the end of this hole. So we can see this wire. So this cathode it is fed towards the end of the nozzle. Okay, so mouth of the nozzle it is fed. So this is the glass capillary here. So this the electrolyte is flowing through this capillary, the high velocity, and this is the at the center. This wire, cathode wire, is used at the center. So two types of electrolyte is used in case of electrostream drilling. So HCl, hydrochloric acid, which is used for aluminum or titanium, but sulfuric acid H2SO4 it is used for carbon steel, cobalt steel and stainless steel for machining this kind of material. So this kind of ram is used if you are machining, you are making a hole which is inclined to the top surface. Okay, so this kind of inclined holes also you can generate. So process performance used for drilling high aspect ratio holes. Penetration, for penetration drilling 40:1, so length to diameter ratio of the holes are 40:1, and for dual drilling it is 10:1. Machining rate is 1.5 millimeter per minute. In special case, 96 holes have been simultaneously drilled in a turbine blade in 1.5 minute. Shallow holes up to an angle 75 degree from the normal to the workpiece can be made. Tolerance is up to plus minus 5% of the diameter of the hole to be machined, but it is less than 0.025 millimeter. It should be less than 0.025 millimeter. Surface finish achieved is 0.25 micron to 1.67 micron. Taper can be controlled as 0.03 millimeter to per centimeter length of the wall. So this much is the taper. So these machine components are bar free, no induced residual stress, insignificant heat affected zone, and no tool wear is there. So now another process is there, that is called shaped tube electrolytic machining, STEM, shaped tube electrolytic machining. In electrostream drilling we have seen this aspect ratio of the holes are maintained as 40:1 maximum. But in case of electrostream drilling, the aspect ratio of the holes are maintained at around 300:1. So it is very high. For very high aspect ratio holes, to making very high aspect ratio holes, Shape tool electrolytic machining is used. STEM is used. Small diameter hole in electrically conducting materials, high aspect ratio 300:1. Round or shaped holes can be any kind of holes, can be in turbine engine headofoils, can be generated. So these kind of holes can be used in aerospace industries or difficult to machine materials, superalloys. Acid-based electrolyte is used because this acidic electrolyte, it will react with the material. So electrolyte will react by electrochemical dissolution, and whatever these debris particles are there, metallic hydroxide or sludges are there, it will dissolve into the acidic electrolyte so that it can be taken out from the machining zone. So only 10% of the 10% of the electrolyte or 10% concentration of any H2SO4 HCl is used as a electrolyte. So these reaction products are actually dissolved. Shape tube coated exterior surface. So here actually this tool, actually it is metallic tool is used. Generally this titanium tool is used. But here this outside surface of the tool, actually it is coated. Only machining is done by the tip of the tool. So this tip of the tool is not coated, but outside surface of the tool, hollow tool, is coated. So low voltage around 5 to 15 volt is applied. At higher voltage, it will actually, metal removal rate will be higher. So it will damage the whatever coating material is there, it will damage, delaminate the coating material. Also, if it is delaminated, then there will be stray cutting of this. Because of stray cutting, you cannot generate high aspect ratio holes. Non-uniform holes will be generated. And there may be, if at higher voltage, there may be boiling of the electrolyte may be there, or there is a plating of the electrolyte may be there at high voltage. So maximum feed rate it is achieved is 5 millimeter per minute, and normally is 1.5 millimeter per minute. So this is the schematic diagram. So these are the metallic tools, hollow tubes are used, metallic hollow tubes are used. So this is the excited view. So here you can see this kind of small corner radius is generated on the workpiece. So this, that is a constant feed actually given to the tool here. So overcut, control applied voltage and electrolyte flow velocity so that overcut can be reduced. Taper operand 0.015 millimeter per centimeter length of the hole. Surface finish is in between 0.8 to 3.1 micron. Electrolyte is 10% H2SO4 or hydrochloric acid in water. Temperature is maintained from 37 degrees centigrade to 49 degrees centigrade so that these electrolytes electrical conductivity can be maintained. Constant inter-electrode gap can be maintained by using a servo system. Multiple electrodes with varying shapes, 100 holes simultaneously can be generated. Proper exhaust system should be there so that whatever these gas bubbles or reaction products are generated, that can be released from the exhaust. So extract corrosive electrolyte, mist and hydrogen gas using the exhaust system. So after drilling, these workpieces are thoroughly actually washed by water to neutralize the remove the residual acid, because acidic electrolyte is used for machining purpose. Tube material, it is pure titanium to resist any kind of corrosive action. So it is tube is made of pure titanium. Coating of the tube saves from the attack of the electrolyte and eliminates stray cutting to the wall of the hole. Pinhole scratches or delamination in the workpiece material or coating material would result in the stray cutting. So to obtain best results, tip is decreased at an angle of 10 degree. So this hollow tube, there tip is decreased at an angle of 10 degree. The increased productivity are to make the process more versatile. Tips may be made of different shapes and size even in multiple hole machining. So to make the tips independent and separate, bead type of tube also may be used. This bead type of tube, because machining is done by this tip, so in that tip you can use a bead type tube. Okay, so it can be connected to a non-conducting shaft. So bead type of tube of the desired shape and size, and then fastened or by threading or otherwise other method to the bead holder of the electrode. So after this electrochemical machining. Okay, thank you.